welcome back. Today we're going to do the lab for Chapter 7, and this is the chapter on nonlinear modeling and additive models. Okay, as usual, we'll do our inputs at the top. We won't dwell on the ones that we've seen before. We'll look at some of the new imports. So one of the new imports is going to be from this Pygam library. That's the library that we're going to use to fit generalized additive models. And then we have, we're also going to talk about splines in this lab, and we'll talk about two different transformers for B-splines and natural splines from ISLP, and their associated helpers for model spec, this BS and NS function. We also have a few utilities that we wrote to help with the Pygam package. Okay, so the lab starts off with a sort of review of polynomial regression. We saw polynomial regression in Chapter 3 already, but we're going to use that to compare that to splines and later to additive models. The data we're going to look at is trying to predict wage. I think this is the Mid-Atlantic wage data. We're trying to predict wage of workers as a function of different attributes, and we're going to mostly look at wage as a function of age. There's also going to be education level as another feature. There are several other features you can find in the documentation. Okay, so having fit polynomial regression, we're going to want to look at the fit, because one of the nice things about additive models is for each feature you can make a plot of the estimated effect for that variable. So we'll first take a look at the fit for using polynomial regression. So there's a bit of a boilerplate code here to try and make these plots that I'm not going to dwell on. We're going to use a function here in this lab because we're going to plot several things as a function of age. We wrote a little function to make our life a little bit easier. So we're going to change in the function what the modeling, that is what in effect what the model spec is. That's what we call the basis. And we'll evaluate the basis on this age df. This is a grid of regularly spaced values of age we can use to make a plot. So let's just take a look at the fit of the fourth degree polynomial. And we've also included error bars. One other thing about this plot of note, if you want to read the function that produced it, because we have quite a few points, to try and get a sense of, in the scatter plot of density, we've added some opacity, so an alpha channel to the points. So this is alpha, I think 50% and 40%. It gives some sense in the scatter plot of how many points are in different regions.
I'm sad to say that I'm on the beginning of the downward curve of that wage plot, Jonathan.
Oh. Well, it doesn't go down too quickly. Right yet. Okay. So in building a model like a polynomial regression, we often maybe want to determine the order of the regression model. One way we could do that is using something like the cross-validation, as we had seen in Chapter 5. Another way we might do it is by looking at a statistical measure of how much the fit improves as a function of degree. And we'll do something like this later in the generalized additive model, where we compare having no fit for age not being in the model, linear, and then with an additive function. So what we're doing here is we're using this ANOVA LM function, which is something we saw in Chapter 3, to compare the models as we increase the degree of the polynomial. And just a quick takeaway, we're looking at these F statistics. A large F statistic means the transition from one model to the next is a significant improvement. F statistics are around 1 on average, so anything much bigger than 1 is good evidence is evidence that there's an improvement. So we see going from having no age to age linearly as a big improvement, and then quadratic quite a bit, cubic a little bit less, and then the fourth order doesn't seem to really add anything to this fit. Okay, and just a note, you can find those F statistics in the case we only have a single feature can also be found from the summarized table, but let's move on. Okay, so that table we just saw before looked at the effect of changing the degree we model age with, and trying to pick, when to stop increasing the degree. We're not limited to only using age as a feature. We can, of course, do that with other features. So here we've used education, which is a categorical variable. So we're looking at the effect of age allowing for education, and we can do a similar construct a similar table to see the improvement of the fit as we increase the complexity of the age fit. And we do, again, see a big improvement when we go to linear, and still some improvement when we go to quadratic. We haven't gone all the way to the fourth order degree here. Okay, so we've looked now at how to sort of make a flexible model of age for of wage as a function of age, I should say. Another thing we might consider is, instead of predicting the wage, we might just try to predict whether they, turn to a binary problem to see whether the worker earns more than 250,000 or not. So we'll call these the high earners, whether they earn more than 250,000 or not. And we can repeat the same process, but instead of using ordinary least squares, we're going to use logistic regression. And remember, this is the GLM object from stats models, and the family is the binomial family. That tells the computer that it's a logistic regression. So this is going to, if we fit this model and summarize it, it will look a lot like the linear regression fit, though now we're trying to predict a binary outcome rather than a linear outcome. So we can similarly make a plot of the estimated effect. And let's take a look at this plot. We have blue curve is the fourth order polynomial we fit with standard error bars.
Oh, now my H category looks much worse.
Yes, yes. Maybe I spoke too soon about the degree. So a few comments about the plots. So we don't see the scatter plot that we did when, and that's because we've changed the y-axis here. We're trying to predict whether something, a binary outcome. So we really have cases that are 0 and cases that are 1. Though here we've truncated the axis to 0.2 just so that we can see this fit here. So we've labeled the points up here. These are the age values where there's a tick here. These are the age values where we had high earners, and these are the wage values of the low earners. And a similar device to get a little better visualization is to add a little bit of jitter to the x-axis here to try and get a sense of how dense the ages are, because the ages are actually just integer values, so you can't really see anything by the ticks.
And notice how wide the standard errors are on the right-hand part of the plot.
Mm-hmm.
It usually means there's very little data there. Often you do get wide standard errors at the edge of the range, but if there's very little data, then it gets even wider.
Yes, and I'll just add one comment. Another facet is if everyone is a low wage earner, then that's another sense for binary classification that there's low data.